talk about generic partially static data.
So hi, I'm David Kalapir-Meshinak from University of Cambridge, and I wanted to talk about something a work in progress I've been doing with Jeremy Yallop, also from Cambridge, which we call generic partial static data. I want to explore a little bit of background because it sounds super obscure, so I guess I need to tell what is going on here. We work in multistage programming. Now I assume many people kind of know what this is. As a refresher, it's when you partition a program execution into phases, such that an early phase produces a program which will then be executed in the second phase. So the result of an evaluation is another program. And it can be seen as a form of metaprogramming, or it can be seen as a form of partial evaluation, because it's a little specific as far as metaprogramming goes. Metaprogram cannot actually inspect the program it's constructing. And the multistage programming we're using is the one implemented by BR Meta OCaml, so we're working on OCaml. And in doing multistage programming, the concept of static and dynamic pops up very often. By static, I mean something that's available in the presently evaluated program right now, in the program we're talking about. And dynamic is part of the next stage program, so it's not currently available. It sort of represents the future. I can give an example of a stage program, and it seems to be the mandatory example from sort of stage programming and partial evaluation literature, a power function, and in particular the one that's not efficient because it's linear in the exponent. So this power function essentially unrolls the exponent and constructs a program which is a successive multiplication of, which contains wholes and will multiply whatever is given once this is converted into a program, however many times E tells it. And as you can see, it's a little kind of tricky to see what's going on modulo the syntax. I don't know, should I perhaps tell you what the syntax means? Brackets lift stuff from the present time to the future. So dot brackets 1 is 1 in the next stage, and dot tilde puts something, splices something that's available right now, the result of a program available now into the program that's part of the future. So directly staging programs is sort of tricky. It doesn't really work out too nice, and we're attempting to abstract this away. And one of the particular problems is that because of a dynamic value instead of a larger term, sort of infects the entire term with its dynamicity. Oftentimes one needs to do CPS conversion, so this kind of complicates any code you're making that's staged. So there's this concept of partial static data, which is where we try to focus on data and not directly on the code. And this is done by allowing datums to classify between values available right now or in the future, so static and dynamic. And the prototypical example is this alpha PS, which either contains an alpha right now, or it contains a program which can be evaluated in the next phase, which will give an alpha at some future point. And there's an example of a list, which is partial static, but only in the spine, not in the alpha parameter, which pretty much looks like a list. There is a null case and there is a const case, but then there is the dynamic case, and the dynamic case contains the rest of the list. But it's not the same data type, because once we go into the future, we cannot keep on going into the future indefinitely. So it contains alpha list code and not list partially static. We can do basic operations on data types transformed in this way. So for example, this is a version of concat, which pretty much does what you would expect it to do. When it hits the dynamic case, it lifts the entire right-hand side list into the future using the function din, and just produces a program which will do everything in the next stage. In the other two cases, it's pretty much concat. And then we have partially static data types. Usually people do partial static data transformation kind of ad hoc for the problem at hand. And partial static data types is something that's been described as a general transformation for on-algebraic data types, for completely transforming them into the partial static version. And it pretty much works like you would expect it to. Products need to account for the possibility of every combination of components not being available right now, and the sums can either be fully unknown, or we can have a known constructor with then a product which is partially static. And it looks a little like this. So for type T, which has only two variants, the first one is a product of two integers, and the second one is a recursive point. Its partial static version is either completely unknown, so we will know T in the future, or there's a number of possibilities for the first constructor where we either know both or only one or neither right now. And then for the second constructor, we either right now know a partial static version, or we only have the static version in the future. So this is sort of how the transformation works out. And as you can probably tell, manually transforming data types through in this way is still tedious, still not really nice to use. And writing programs over those is also not super user-friendly, programming-friendly. So we're wondering whether we can apply generic programming techniques to sort of automate this transformation and to provide an interface for manipulating these partial static data types, which is kind of oblivious to the transformation to as much as it's possible. And in order to do that, instead of focusing on every single combination which you could get from sums and products view, for example, repeated applications of products or of sums, we want to focus on the type parameters here. And essentially, the partial static transformation can be obtained by a particular fixed point operation over the open recursive version of the data type. Here is an example of an open recursive list, which never mentions itself. So something from the outside will hopefully fix point it in the parameter beta. So given that we are kind of describing this transformation through its fixed point structure, we started playing with what's sometimes known as origami stub approach to generic programming, which also starts with open recursive definitions of data types. And here's an example of how one would do origami in OCaml. There's this interface, which is analogous to Haskell type class bifunctor, which gives a type with two parameters, which is the open version of a one-parameter recursive data type, the second argument being whatever will be fixed pointed through. And the one function sort of takes two functions operating on both components and applies them inside, reconstructing one layer of the type. Then we somehow introduce a fixed point, in the case of a camel, through a module, through a functor. And then we can define the generic folder over anything that exposes a bifunctor interface, which sort of needs a function which can operate on a single layer whose recursive point is a partially built result, and fold that into a complete result, and it gives back a fold over the entire fixed pointed thing. As a note, I'm using a variant of OCaml, which not only contains stage programming extensions, it also contains modular implicits. These are the color braces here, and you can roughly read these as a Haskell type class, more or less. So this is how one would do an origami list, for example, in OCaml against those interfaces. We define an open recursive version of a list, provide a map function which doesn't do too much, and with that we get operations, whichever operations our generic programming system gives us. Now we're trying to kind of take that fixed point approach and apply it to partially static construction. And in particular, if we limit the number of stages to 2, a slightly skewed structure emerges. So if we take a simple partially static type and extend it with 2 parameters for 2 different types, one in the static and one in the dynamic case, we can write the partial static fixed point through, as shown on the slide, which really means that its static, currently known recursion goes back to the same partial static data type. But once we go into the future, everything that's left in the next stage is only the static version. Otherwise, we would have an unbounded number of stages of evaluation. So this is kind of the gist of the transformation as far as the fixed point is concerned. And then if you work it out analogously to how origami works, you get an augmented form of a bifunctor, which has 2 different maps. One is purely for stuff known now, for the static case, and the other one looks roughly the same for the kind of dynamic case, except it deals with functions which return stage dot or code fragments, and in itself it returns a code fragment. And this is the basic thing that's needed to plug into the rest of the system. We're describing individual data types through this partial static interface, which sort of describe the interaction between a static component and how to lift it into partial static version, dynamic component and how to lift that one into partial static version because a PS version contains either, and how to take a partial static version, unfold the decoration, and recover a code fragment evaluating to the ground type. So with this, we kind of translate the fixed point we had in mind to this functor, which is a little involved, but it really just does the same construction where the fixed point in the static case goes to the same partial static data, and the fixed point in the future goes to the simple static version to limit the number of stages, and we add the operations that convert this into full PS interface. And with that, we can derive something like a fold over partial static data, and this is the signature, and I will not bother you with the full implementation. It gets a little noisy. It looks very much like the other kind of fold, but it needs to take explicitly into account for the possibility of what happens when there is a dynamic component. So it needs to take a dynamic function operating on dynamic elements, and yeah, it's kind of a mouthful. So we started trying to replicate origami in the context of the partial static construction, and it does work basically. But it's not clear whether this is the right way to cut the problem, because if we either have to explicitly deal with the possibility that things are dynamic and have to explicitly provide functions for the dynamics case, or if we kind of uniformly treat that, we end up emitting closures into the next stage. And this is the cross-stage persistence problem. We can't currently simply run such a meta program, generate an object program, persist it into, say, a file, and then compile it separately because we can't take closures across stages. So the trade-off is really between specifically accounting for whatever the multistage programming is and relying on cross-stage persistence. And also, we'd like to see if we can generalize that slightly more so that we lose, so that we don't specifically talk about multistage components or multistaging, because if we express the code, the transition into the future, as simple functor, we can simply use a traversable and reconstruct most of the operations. But then the problem is we get a lot of lambdas which we can't persist and we can't separately compile. So that's in essence it. Thank you.
So you didn't really tell us why you want these partially. Can you give us any examples where a data structure which was partially staged was useful? Do you have any examples?
True, I didn't. I have a couple of embarrassingly small examples. My favorite is a version of FFT, which operates over a very nice simple data structure and a nice functional expression of an FFT. And nice and simple data structure contains potentially dynamic values. So once applied to it, the result is this another structure which can be unfolded into program, which is kind of the loop unrolled version of the original program. So starting with a program that looks like a nice high-level functional thingy, we end up with something close to specialization or partial evaluation or so. So I haven't seen too many examples, and the hope was if we could get this running, we can actually produce some more significant examples. But the ones I've seen are sort of a way to write very high-level functional things and then have them unrolled into very fast things.
Okay, any more questions? Okay, thank you very much.